Okay, in this video we're going to go over the 4.1 exponential functions. So the key thing is to recognize an exponential function. So an exponential function has a base and then its exponent is a function. Okay, so that's where the x is going to be. So listed in this box are examples of how you can work with exponential functions. So I'm going to write know this. So look at this, make sure you understand what you're seeing. This is also on page 246 in your textbook, so you should go through and review that as needed. So a couple of big picture things. If you have the same base, you can write the base one time and add the exponents. If you have the same base that are divided, whereas in example I, it was multiplied, you can write the base once and subtract them. Okay, so 1 and 3 are product and quotient respectively. Okay, 2 is just location, location. So if the exponent is negative and you wish to make it positive, change its location. So in this first example, b to the negative x is in the numerator. Putting b to the negative x in the denominator changes the x to a positive. So you should be familiar with that. Here is an example in 4 of power to power. So you have the base, and then that expression is raised to the power of y. So in order to do that, you're going to write the base once and multiply the exponents. Notice that that is different, so 4 is different than 1. All right, let's see, 4, oh, I have 4 twice, that's not good. This should be 5. So 5 and 6, you really need to look at them and make sure you see what they're doing. Here you have 2 different bases, the same power. So you can bring the bases together and then raise the whole thing to the power. Usually your brain is good going one way, but not the other. So make sure that you can do this and recognize it in either case. Same thing for 6. You have different bases. One is A, one is B, but the power is the same. So again, make sure that you understand going both ways. All right, going on down to number 1. It says, note that the property, so let's see which property I mean. I think I mean 5, so let me change that to 5. Can be used to change the appearance of an exponential function. Given this, can a function such as, oh, maybe I didn't mean 5, maybe I really meant 4. So let's look at that. Yes, so I really did mean 4. So let me erase that, and we'll go with 4. Okay, so the question is, given this, can a function such as 5 to the 3x be written in the form f of x equals a base to a power of x? And if so, what is b? So what you can do is you can say, okay, I'm going to write this again, f of x equals 5 to the 3x. So I'm going to box 5 to the 3. 5 to the 3 is 125. So therefore my function can be written with a base of 125 and a power of x. So that's how you do that. So make sure you're comfortable with that. Okay, moving now to number 2, it says use the concept of unique base to solve this equation. So here's an equation, and we have 7 times 2 raised to the power of 6 minus 3x, and that has to equal 28. So when it says solve, it means find out what x equals. So let's see how we can possibly get to a unique base. How about if we divide both sides by 7? Divide by 7, divide by 7, and I'm going to rewrite it over here. So now I have 2 raised to the power 6 minus 3x, and that's going to equal 28 divided by 7 is 4. So do I have a unique base? Which means, do I have the same base? Not yet. But can't I make that 4 into a 2 squared? So let's do that. So I'm just going to do it right here in the interest of space. So instead of writing the 4, I'm going to make this 2 squared. Now we have the same base. In order for these two things to be equal on either side of the equation, the only way that's going to happen is if the exponents are equal, because we already have the same base. So take your exponents, and your exponents are going to be 6 minus 3x, and set it equal to 2. So I'm going to do this up here. So 6 minus 2 equals 3x. Whoops, sorry. Let me go back. Okay, so that should be an x. Okay, so 6 minus 2 is 4. So if 4 is going to equal 3x, that only happens if x is 4/3. So that would be my answer. Okay, so that's using unique base. So I got them to the same base, and then once the bases were equal, I set my exponents equal and solved. Okay, the last one here, number 3, says, use property I to find the missing factor. So let's look at that carefully. I have this expression right here, and that equals 5 to the x times something. So if I use property I, which tells me how I can relate equal bases, what if I put a 5 here? So, whoops, right in here I'm going to put a 5. Okay, 5x times 5, this is 5 to the 1, that would equal 5x plus 1. But I don't want x plus 1, I want x plus 7. So I'm going to make this equal to 5 to the 7. So 5x times 5 to the 7, write the base once, which is 5, and add the exponents 7 plus x, I get that. Okay, so then I'm going to expand beyond this paren. So I'm going to put down my operation, so that's a negative. Put down another base of 5. So 5x times 5 gives me 5 to the x plus 1, but I want 5 to the x minus 3, so I'm going to raise this guy to the minus 3. So that's an example how you do that. Okay, that operation is a subtraction. So let's make up another one. So how about if I had something like 6 to the 5 plus x plus 6 to the negative 2 plus x, and I wanted you to factor it. So I see they both have a base of 6. I see they both have a common power of x. So what if I say, take my 6, raise it to the power of x, put an open paren, to get this first term back, I'm going to put 6 to the 5. Do you see why? Because 6 times 6 to the 5th, when they both have the same exponent, you're going to add those exponents, so x plus 5 gives me the term I want. Then put in addition, another 6, I already have the x, I need a negative 2 here, and now I'm set to go. So that finishes the first page of the notes. Let's go to the second page. Okay, in this second page, we're going to look at these graphs. These are exponential graphs. So notice the graph on the left is y equals 3 to the x. Notice that y equals 3 to the x has a y-intercept right here at 1. Why is that the case? Well, look at this. If we have y equals 3 to the 0, anything raised to the 0 equals 1. So therefore, if x equals 0, then the y-intercept is going to be 1 because y equals 1. So that's a good landmark to see. Look at figure 4 now. We have lots of different shapes. They're all exponential. They're not all exponential growth, however. Things I'm noticing, y equals 5 to the x is the steepest. So if the base is 5, I have a pretty steep curve compared to y equals 1.8 to the x. Here the base is not as large, and therefore the function is not as steep. And then look below it at y equals 1.1 to the x. The base is less than 1.8, and therefore the curve is less steep. Notice that all of those curves pass through, you guessed it, the point 0, 1, and that's because anything raised to the 0 power equals 1. Okay, on the right, so in the first quadrant are all exponential functions. Look at the second quadrant. Do you see if you have a base less than 1, you don't have exponential growth like we did in the first quadrant, but you actually have exponential decay. So if your base is less than 1, you are going to reflect your curve around the y-axis, and that denotes exponential decay. So in terms of observing things, you would write those observations down below. Okay, another thing to notice. Each of these exponential functions, whether they be exponential growth or exponential decay, each and every function is asymptotic to the x-axis. If it's asymptotic to the x-axis, there is no critical value, or there's no root, we should say. So there's no root if it's exponential to the x-axis, right? The function can never ever go to 0 because you can never have an exponential function that when you raise some base to a power, you get 0. Will you get close? Yes, you will. But will you ever actually get there? No, you will not. So each of those functions is exponential to the x-axis, and therefore there are no x values. There's no x-intercepts, I should say. No roots of those functions. So those are things you should write down under observations about this graph. Okay, your job now is to complete a mock test based on this information, and then you're going to look at the homework for this section, which asks you to do page 248 to 249, 3 to 42, multiples of 3. And you're going to check your answers to all the odd problems in the back of the book before you move on.